Hey guys, Snake here, and today's video is a very significant one because today we are going to look into the foundation of computers, that is logic gates. So, without further ado, welcome to the world of logic. So guys, when we are trying to learn something, there are two scenarios that we must consider in our approach basically. The first case being that trying to understand the core principle of the concept that we are trying to learn. And the second is basically contrast, or in simpler terms to say, the difference and or similarities with a different concept or a different analogy to use. So first we are going to consider the core principle to understand logic. Okay, let's look at it with an example. Okay, say there is a party going on. Okay, and I want to go to this party, but I don't want to go to the party alone. I want to be with my friends there. So let's say I call two of my friends, friend A and friend B, and I want to see whether they want to go to the party or not. So you see, naturally two scenarios come up. In the first case, say friend A and friend B both want to go to the party. Then only I will go to the party. If none of them or either one of them is not going, then I will not go to the party. So I'm going to emphasize on the idea of and. And in the second scenario, let's say either friend A or friend B is going to the party. So then I will go to the party because I won't be alone then. Emphasize on the word or. Okay guys? You see, at the heart of it, all I am doing is comparing the decisions made by my friend or the choices they have made. And this is the heart of logic operations. You see, you can turn this example into a basic electrical circuitry as well. Say there are two wires. Okay, let me draw it first. Say this is wire A and this is wire B, and the output is wire C. So you see, like in the previous case, in the example, there will be two scenarios. Let's write them down as and or. And based upon these two scenarios, I'm going to compare whether there is current flowing through wire A and wire B. And based upon that, I'll make the decision, or the circuit will make the decision to send current through wire C or not. And that is what it is. This is the basic core principle of logic operations. You see, now that we've seen that, we also have to see it in the light of contrast, say through a similarity. And I think in mathematics you are familiar with the operations, say less than, greater than, and equal to, right? Where you basically compare two numbers, you say a1 and a2. This is what a logical operation is, though a modified version. In the mathematical case, you are comparing numbers, and in this case, you are comparing signals, you are comparing current through a wire, you are comparing inputs basically. And that is the core thing to get about this. Now, there is a third scenario as well. You see, let's say Karen, a person whom I do not like, has visited the party. So you see, I do not want to go to the party then. So that means if Karen goes to the party, I will not go. That means it is a scenario of opposite. Emphasize on the word not. And this is the third logic operation that you have to know about. So there are three logical operations: and, or, and not. Guys, working with plain English will become cumbersome after some time, right? You can see that. So you see, the scientists or the circuit designers use symbols to represent these logical operations or these circuitry components basically. Likewise, in mathematics, you see they use greater than, less than, greater than, less than, greater than, and equal to. Likewise, here there are circuit symbols or diagrams to represent these operations. We have seen that there are three, right? And, or, and not. So let's see their circuit diagram. Okay, now AND is represented like the symbol D. Okay, where these are the two input A and B, and this is the output. Okay, in case of OR, it is like an arrowhead. Okay, they meet at a point, and that is the output, and the two inputs are A and B. And in case of the NOT, it is basically a triangle with a circle in front of it, and it has only one input, say A, and the output is B. Okay, though nowadays there are computer applications out there that has automated the process, so you don't have to do this by hands anymore. So yay us. So guys, this one here, as you can see, it's a 7432, and this is basically an OR gate chip. Okay, now you will see under the light here that there is a notch at the front. This signals the direction, or from which direction you should count the number of pins. So from the direction with the bottom one is pin number 1, and it goes from pin 2, pin 3, and then up to pin 7 here, and then pin 8, pin 9, pin 10, and up to pin 14 here on this side. Okay, this is a 7432 as you can see in the video. This one here is the 74, as you can see, the 7408. This is the AND gate, and the same number of pin apply, and there is a notch in the front of it basically. And finally I have the OR chip. This is a 7404, and the same logic still applies. There is a notch in front of it, and you count 1 from here. It goes all around basically. Now I will show you this in action as well, but for now this is it. So let's get translating those plain English logic into mathematics, or in our case a mathematical table that we call the truth table. Okay guys, so first let's write down the inputs. Okay, A and B. Now since there are two inputs, there will be 4 possible permutations of it. That is basically 2 to the power of 2, right? So let's write them down. 0 0, 0 1, 1 0, and 1 1. You can actually relate it to the first example that I showed you. This is, say, the input for friend A, and this is the input for friend B basically. So I'm going to first see the operation of AND, and that is represented with a dot basically, A dot B. So let's find the truth table. Okay, when none of my friends are going to the party, I will not go to the party. Okay, when only one of my friends are going to the party, in that case also I will not go to the party. Only in the scenario when both my friends are going to the party, I will go to the party to enjoy basically. Now there is a key takeaway here. Okay, something to observe here. You see, in this case I have represented me going to the party as the value 1 and not going to the party as 0, but I easily could have chosen to use 0 for me going to the party and not going to the party as 1. So you see, then the truth table would have become 1 1 1 0, and you see the circuit has been designed by a human being, and there is nothing wrong in representing in this reversed way, as long as you're clear about the logic that me going to the party has to be represented by 0 and not going to the party as 1. Because you see, if you know how to work with transistor, if you can build it, you can easily build this second circuit actually, and you can name it, you can give it a different name and release that logic gate into the world. But you see, since the input are 0, I want the output to look something similar as well, and say in case when it is both 1, the output is also 1. And this is the reason why this is chosen as the standard truth table for the AND operation. It easily could have been this, and you are free to change anything you want. if you know how to work with transistor and design your own circuit, but that will not be the standard. If you want to talk with other people in terms of the truth table, you have to understand this or have to use this that is chosen basically for the world to work with. Now let's look at the OR operation. Okay, now the OR operation is represented using the plus sign. Okay, this has no relation with the addition symbol from arithmetic. It has nothing. It is just the same symbol is being used here. Okay, do not mix it up. So in this case, let's translate it in terms of the first example. Okay, when none of my friends are going to the party, I will not go to the party. But if one of my friends are going to the party, then definitely I will go to the party because I won't be alone there. And if both my friends are going to the party, then a definite yes that I am going to the party. And the same logic applies as well. You see, I have represented me not going to the party as 0, but I could have easily represented with 1. And the reverse circuit is also a valid circuit if you can design it. But again, for the same standardization reason that the inputs are 0, so the output should be something similar. That is why this is the standard truth table for the OR gate. Okay, guys? Let's look at the final logic operation, okay, the NOT one. And let's see it in terms of the Karen scenario. Okay, now let's consider the input as K, and we represent NOT either with a bar above the head or like this. Basically it is called the complement. Okay, so with one input there are only two possible combinations, right? Either Karen is going to the not going to the party, or Karen is going to the party. In this case, if Karen is not going to the party, then I am definitely going to the party. And if Karen is going to the party, then I am not at all going to the party. And that's just flipping the values basically. So guys, right now I'm working with the OR chip, basically the 3-2 chip. Okay. Now this breadboard is hooked up with an Arduino Pico, and the first row here is voltage 5 volts, and this is the ground row. Okay. Now as you can see here, this wire connects the chip with the 7th pin. The 7th pin is basically the ground pin, and that is connected to the ground. Whereas the 14th pin up here is the VCC, and that is connected to the 5 volts. And that is required because internally the circuits are transistor based. Okay, so you need a 5 volt supply or a VCC supply to basically make the chip work. Okay, now currently I have hooked up the first two input, that is pin 1 and pin 2, to the ground. Okay, and the output is the third pin that goes to the LED and then to the ground. Okay, now when I connect this to the power supply, okay, see it's turned on now. You see, since both inputs are connected to the ground, that is equivalent to the inputs being zeros. So that is why the LED is not glowing. Okay, but now I am going to change one of the inputs basically. Let's first turn off the circuit. Okay, now I take the input, first input, and then I connect it to the 5 volt supply. Okay, and let's see when I turn it on. See, the LED starts to glow, because as per the truth table, remember that when input is one of the input is 1, the OR will output 1 basically, and that is why the LED is glowing right now. Now guys, there are 3 other gates as well that cover the domain of logic gates. Okay, they are basically NAND, a NOR, and a XOR. Okay, a NAND gate is basically not AND, and NOR is not OR. So their truth table basically looks like this: 0 0 0 1 1 0 1 1. Remember the alternate circuit that I was talking about? Well, you see, people actually have come up with that and designed that circuit as well, and they are basically these gates. So a NAND operator is basically the same as the AND operator, but the output is complemented. So when both values are 0, the output is 1, and when any one of them is present, then also the output is 1, and finally when both are 1, the output is 0. And likewise, the NOR operator is also similar to the OR gate or OR operation, A plus B, but the output is complemented. So that means when both input are 0, the output is basically 1, and in any other scenario, when there is one input that is present with 1, then all outputs will be 0 basically. That is the same as the alternate circuits that we talked about, but they have already been designed as well. So better luck next time, guys. Now for the final gate, the XOR circuit, this is a very special gate. This is something that is equivalent to the equal to comparison in arithmetic. Let's see the truth table first, okay guys? It is, the XOR operation is represented with a plus encircled and then B. This is A XOR B basically. And in this case, it basically compares the two input, and if the inputs are equal to each other, then the output will be 0. But if the inputs are not equal to each other, then the outputs will be 1. And like I said, it is something that is equivalent to the equal to operator in arithmetic basically. Now let's look at the circuit symbols as well, okay? Now the NAND gate is represented similarly to the AND gate as a D, but with a circle in front of it, okay guys? So this is the input A and B, and this is the output, okay? And the NOR operation similarly is same as an arrowhead as in case of OR, but with a circle in front of it to represent a NOT operation. So this is input A and B, and the output is C. And in case of the XOR, it is similar to the OR operation, but there is a parallel curve in front of it. And this is the XOR gate basically. With this, all the logic gates are covered, guys, okay? So that covers all the building blocks of logic operation, okay? And with this, I end my video today. Please put all your queries down in the comment section, like and share my video, and please subscribe to my channel. And with one last thing to say, to learn, never memorize. Bye guys.